Good evening, everyone. Thank you so much for coming to hear me speak, to share my personal journey, to understand how complexity arises in our universe. So, a little bit of my background was given by the moderator, so thank you very much for that. But I would like to point out that if you take a look at the three images here, apparently I started out as very unique but not very valuable, ended up as very valuable but not very unique. So that's kind of sad. I've got to change the slide moving forward, and I've learned so much from TEDx so far. But that being said, I did start out in the main asteroid belt, ironically. My PhD work is in the development of ion engines. And the whole purpose for the Dawn mission, which is currently out at a protoplanet right now called, first it went to Vesta, then it went to Ceres, is to understand how our solar system evolved by looking at objects in the solar system which are very ancient and seeing how they differentiate to form planets. 5 years in from that, I went to the surface of Mars with the Curiosity rover to understand how the planet evolved. Could the planet once have been habitable? What happened? Why is it not habitable today? Or could there even be life form somewhere in the subsurface of the planet? Moving forward another 5 years, I decided to do something very different, which was to explore atomic physics, quantum mechanics, because truly our world is comprised of very complicated things such as subatomic particles, atoms, molecules, cells, tissues, and organisms. And we understand things by understanding the fundamental physics behind them. I'll talk a little bit more about the Cold Atom Laboratory mission going forward to see how that can actually show you the insights into our planet. But then I decided that I wanted to come back down to Earth, from low Earth orbit down to the surface of the planet. And I wanted to take my engineering skills to do something which would help some of the problems here at home, such as climate change, such as difficulty accessing transportation systems which are both efficient as well as convenient as well as cost-effective for society. And so that's why I came back to develop the Hyperloop. And those were my quests for answers, but we should take one step back, which is understanding the nature of the universe. The universe as we know it is 14 billion years old. It started out as a ball of energy, incredibly warm, and started to expand. And as it expanded, it formed complexity. A blink of an eye after the formation of our universe, we started to see the first subatomic particles. A blink later, we started to see the first atoms. A couple 100 million years later, we started to see the first stars. A billion years later, the first galaxies. And today, we have clusters of galaxies. And today, we have some of the most complex systems that we've ever seen, which is the organisms that inhabit this planet, which includes us. We are, by definition, complex beings. And so by understanding the nature of matter down to the subatomic scale, all the way up to the galactic cluster scale, you can understand how complexity arises in the universe. But when you do that is you take a look at the phenomenology of matter. Everyone's familiar with particle accelerators. Everyone's familiar with CERN, which is where you speed up particles to understand basically what happens when you approach the speed of light, whether it's the Higgs boson or the God particle. There's another way to understand the complexity of matter, and that is to slow things down. So back in the 1800s, Lord Kelvin invented the Kelvin scale, which took a look at the amount of energy substances had, which is a function of their temperature, which is a function of their speed. When you slow things down, you get to colder temperatures, to lower speeds. And so at absolute zero, the minimum energy state, you are essentially motionless. Move forward another 100 years, Einstein and Bose developed a theory called BoseEinstein Condensation, which explained that when you had a gas, took it to very cold temperatures just above absolute zero, it would form another state of matter called a Bose-Einstein Condensate. But back in the early 1900s, they had no way to create this state of matter. It was only moving forward many decades later with the advent of new technologies that we could actually demonstrate this new state of matter. This is important because when you get to really cold temperatures, you actually tend from chaos to order. And when you tend to order, you create properties that you can develop new technologies which can actually be more efficient. And I'll talk about this a little bit. We're talking about superfluidity and superconductivity. And so what does this mean? How can we achieve this state of matter, this ordered state of matter at just above absolute zero? Well, everyone's familiar that light has both a particle and a wave nature. And all atoms have within them an atomic fingerprint. This atomic fingerprint basically says if you can send a series of photons at a very specific wavelength or frequency, you can actually make those atoms absorb that light or emit that light. If you do it for atoms that are coming towards you and they absorb this energy, you can actually slow them down. If you slow them down to almost stopping, you achieve a state just above absolute zero, and you can achieve a Bose-Einstein condensate. So when laser technology was developed in the 1950s, scientists then took that laser technology and decided, well, what if we try and slow down atoms using this laser cooling technique to create a Bose-Einstein condensate? And it was done. Laser cooling won the Nobel Prize. The development of a Bose-Einstein condensate won the Nobel Prize. And that's where we are today. But the interesting thing is that if you want to get even colder, you need to combat the pull of gravity. So when you use this laser cooling technique, this ball of clouds that you're firing these lasers into tends to drop out of the field that it's in, and it can no longer expand, it can't get any colder. So the holy grail of creating a Bose-Einstein condensate is to do it in space, to do it on orbit, where you have a microgravity environment. So back in 2012, myself and an atomic physicist colleague at the NASA's Jet Propulsion Laboratory proposed a mission called the Cold Atom Laboratory, which was to create a Bose-Einstein condensate on the International Space Station to make the International Space Station the coldest spot in the universe. It took us 5 years of designing this facility, from an initial one-page proposal to a conceptual design to a detailed design to the fabrication of the hardware, and eventually launching our facility to the International Space Station of May of this past year. It was a labor of love, but we were successful, and we now have that facility on orbit in the International Space Station. So what does that look like? So what it looks like is a facility which normally would occupy the size of this room to be able to create a Bose-Einstein condensate. We were able to engineer a system which could fit inside of a small box, and that box went on the International Space Station. It launched at the end of May of 2018. Astronauts installed it into an express rack, which is what holds all the payloads inside of International Space Station, in June of 2018. And then we started to make Bose-Einstein condensates on orbit this summer of 2018. This is the first time laser cooling has ever been demonstrated in space. This is the first time a Bose-Einstein condensate has been made in low Earth orbit. And what that means is they're now going to achieve even colder temperatures. We're going to be able to explore the nature of the atom in a way that we've never seen before. It will give us insight into a new quantum world. And so my feed forward for the conversation was a quest for answers, to understand fundamental physics, but ultimately, how do we convert that into useful technology applications so that the taxpayers can use it, right, in a way they can use it in their regular lives? And so some examples of that are creating a Bose-Einstein condensate would allow you to create something called an atom laser. We're all very familiar with photon-based lasers, right? We use them with our laser pointers to play with our cats, but we also use them for important things like manufacturing and medical devices. Atom-based lasers will be a completely different type of laser with a myriad of applications which we can't even come up with necessarily right now. Another unique application for this is that a Bose-Einstein condensate is inherently ordered, which means that it is a superfluid and it is a superconductor. If we can harness that understanding to create superconductors, we can transfer electricity over large distances with few losses, which means we can solve the challenge associated with energy production, make it efficient, make it greener, and reduce the carbon footprint. And then quantum computing. Everyone's heard about it. Quantum computing enables faster processing capabilities at lower energy consumption, lower energy dissipation. So we can solve many of the world's technology challenges by having and harnessing our understanding of quantum physics. So I am an engineer by training, but I am an explorer by heart. I do love to travel. And my very famous, most enjoyable quote that I've ever heard is from Theodore von Karman, who is the father of modern rocketry. Theodore von Karman said that science is the study of what is, but engineering is the study of what will be. And what that means is the engineer can take the tools of math and science to create new technologies to solve the world's problems. So for example, Einstein developed the theory of relativity. What is gravity? The engineer has to come up with a way to combat gravity. Einstein also developed the concept of space-time, right? It takes a really long time to travel the vastness of the universe. So what can we do as engineers to facilitate that faster mode of travel? And that leads into the next segue of my talk, which is that transportation technology has actually enabled revolutions in our society from the beginning of time. 3000 BC, the wheel was invented. Without the wheel, people really couldn't push around goods, food. There are people from place A to point B, very, very difficult to do. When the wheel was invented, all of a sudden you had the first mode of transportation. You enabled people to be more efficient in their day-to-day lives. You enabled the populations to grow as a result. Move forward a couple of thousand years, the advent of rail technology, railways. It enabled the Industrial Revolution. The Industrial Revolution is, in what itself it is an industrial revolution. Move forward another 100 years, personal cars. We have enabled mobility between cities like never has been done before. Move forward again, another 50 years or so, the start of air travel across continents, over land masses. We have created a global economy and a global society because of air travel. So transportation technology revolutions have shown us over the course of the past 5,000 years how we can fundamentally change society by developing these technologies. And so I do believe that the next mode of transportation revolution is the Hyperloop, which is essentially space travel on the ground. So in the opening, I'm a massive science fiction fan. Star Trek and Doctor Who are my number 2 things. And so I do like to say that science fiction basically enables a whole new way of thinking of the world. So an author might come up with a new way of doing something, and an engineer can make that a reality. And what that means is that as individuals, we can actually build the future that we imagine. And so if we imagine a better future, a fairer future, a greener future, we can make that happen with our understanding of fundamental physics and with the tools of the engineer to create these brand new technologies to make the world a better place. And so what that couples to is the Hyperloop. So what is the Hyperloop? You've probably heard about it in the news media recently. The Hyperloop is a new mode of transportation. It basically consists of a passenger vehicle, which you can see in the slide behind me, which is magnetically levitating and electromagnetically propelled. All of that is done inside of a vacuum tube. A vacuum tube means that you've removed air from the system. When you remove air from the system, you essentially eliminate aerodynamic drag. Once you've eliminated aerodynamic drag, you're more like a spacecraft, which means you can get to incredibly fast speeds with very low energy consumption. Also, because the passenger vehicle is levitating, you don't have frictional resistance from the ground. So this new mode of transportation allows you to go faster than airplanes at a fraction of the energy cost because you're doing it in a vacuum. So this is smart, right? This is using the concepts of spacecraft technology. This is losing our understanding of fundamental physics, which relates to electromagnetics, and it relates to coming up with a new mode of transportation which is much greener. Now, the primary mode of propulsion in a Hyperloop system is a linear electric motor, which means that this system is entirely electric. It can operate off of grid-based power, and that grid-based power can come from renewables. So you can have a mass transportation solution which is carbon neutral and potentially produces power. So green transportation is the future. And in the test sector, I believe that our job is to make things more convenient for people, to give people new tools that they haven't had before. But I also think we do have sort of an ethical responsibility to solve the climate change problem. So a Hyperloop system, because it's operating off of grid-based power, which can come from renewables, and it can even carry its own solar panels on the exterior of the tube. So in addition to providing power for itself, it can actually put power into the grid. And so this is what we have to think about when we think of green transportation solutions, which is to be carbon neutral, no greenhouse gas emissions, to do what we can to solve the climate change problem. And so build it and they will come. My company that I work for, we actually have built an operational Hyperloop in the desert just northeast of Las Vegas, Nevada. And so what you can see in this graphic behind me is a half-kilometer section of vacuum tube. Within that is a passenger vehicle. Doesn't carry people right now. It's doing technology demonstration. But we've demonstrated magnetic levitation. We've demonstrated the linear electric motor. We've demonstrated speeds in excess of 400 kilometers per hour. The design speed for our system is actually closer to 1,000 kilometers per hour. In order to achieve that, we have to build out our test track a little bit longer to get to that point so that we can accelerate it. But the way that you can demonstrate these new modes of transportation is that you do it with testing. You do it with prototyping. You do it with brand new techniques which have never been done before. And you try and utilize the venture capital community around the world to fund these new transportation developments. And so this is where we are right now. Technology demonstration is done, and we're now shifting over to production design to hopefully implement Hyperloop systems across the world. So, what can a Hyperloop do? It can connect the planet. We can actually have Hyperloop systems across land masses, which gives you more efficient, time-efficient mode of transportation door to door as compared to commercial airline travel, right? You don't have to drive to the airport and check in. You just get on the Hyperloop and go. And it runs with a frequency more similar to metro systems. So that means for you as the end user, the customer, you essentially have no wait time. It's like taking a train, or rather a metro, from city to city. So you can turn basically cities into subway stops or into metro stops. It's a completely different way of thinking about how you can connect the world with this new technology. But to bring it back from where I started, my journey has always been to understand my place in the universe. And in this graphic, what you see here is our home planet, Earth, in the middle, which obviously has a nice set of water, 75% covered by oceans, a thick atmosphere. But at the beginning of our solar system, Venus, one planet in from us, which currently has a surface temperature of almost 500 degrees centigrade, and Mars, one planet out from us, which has a very chilly temperature of minus 150 degrees centigrade, they are not habitable any longer, even though at the beginning of the formation of the universe, they were. What this means is that we can point to our neighboring planets to see that climate change is a planetary phenomena. It is all of our jobs to do what we can in our respective disciplines to generate technologies which can combat climate change, to reduce CO2 emissions, to keep our planet safe for generations to come. So I'll close with one of my favorite quotes from Socrates, is the only thing that we know is that we don't know anything. And that is what drives us to pursue discovery. That's what drives us to develop new technologies, to make the world a better place and build the future that we can imagine. Thank you.